Okay, this is part 2 of 8.2, accumulation in context. All right, once again, lots of words going on here, and this is just interpretation of meaning. So a cup of boiling water is removed from a microwave and set on the counter to cool. The initial temperature of the water, so starting temperature of the water is 100 degrees Celsius. The temperature of the water T is measured in degrees Celsius as a function of time T in minutes. And so this is the temperature of the water after T minutes. All right. So we want to figure out what each of these little expressions actually mean. So this is the big thing, interpreting the meaning of all of this stuff. So I want to start with this one. It looks the most simple. What does T of 4 mean? We know that T is the temperature of the water, and little t is time and minutes. So this represents the temperature of the water at 4 minutes. Temp at 4 minutes. All right. The temperature of the water at 4 minutes is E. All right. Let's look at some of these others. What is T prime at 4? Well, what's T prime? T prime is the derivative. The derivative of this temperature function is the change in temperature over the change in the time. So this would be the temperature in degrees Celsius over minutes. So this is a change. Remember, a derivative is a rate of change. A rate of change is a derivative at 4 minutes. All right, so the rate of change in the temperature of the water in degrees Celsius per minute at T equals 4 minutes. So that's B. All right, here, look at all of these have a nice 1/4. Here, this has a 1 over K, but it has this coefficient in front, and you can see that it matches B minus A, B minus A, B minus A, K minus 0. 4 minus 0, 4 minus 0, okay? All of these, because of that little factor in front, when I'm thinking about my interpretation, I'm thinking average. Average value, all right? The average value. And so you can see I've got all these average. All right, let's see what we've got here. If I'm thinking about units again, this is our temperature function. So this is the temperature of the water, and we're multiplying it by minutes. So this is Celsius times the minutes for dt. And then this is 1 over 0 minus, or 4 minus 0. Those are minutes. So this is 1 over minutes. And what happens here? The minutes end up canceling out, and we're just left with degrees Celsius. All right. So this is the average temperature of the water, the interval from 0 to 4 minutes. The average temperature of the water in degrees Celsius between 0 and 4 minutes. Let's see. All right, so this is an interesting one. I'm seeing start plus accumulation. This is a rate function. All right. So 100 was the initial temperature of the water. You'll notice 0 to K. I said K is what we would call a dummy variable. You're going to see me use that a little bit on occasion. It's saying if we take any time interval from 0 to some minutes, I'm not sure what minute it is, but any kind of K minutes, like 3 minutes or 12 minutes or 24 minutes, this T prime is the rate of change of the temperature of the water. And if we integrate it, we're going to get the temperature of the water. So the starting boiling water at 100 degrees Celsius, and we're adding this accumulation of temperature. So this is actually going to give us the temperature of the water in degrees Celsius at K minutes. G. All right. Again, we've got this factor 1 over 4 in front. All right. And again, anytime you see that factor, that's usually going to have the word average in there. Here we are integrating our rate function. So if we're just thinking about units, this is 1 over 4 minutes. And then T prime is the change in the degrees Celsius per minute. And then times more minutes again. So what we end up with is still degrees Celsius per minute. Average rate of change in the temperature of the water in degrees Celsius. F. Average, this is a rate of change function. Average rate of change. All right. Okay, this, again, we have an interval between 0 and 4 minutes, and this is our rate of change. So this is just like displacement. This is the change in the temperature of the water. This is the displacement function, the change in the temperature of the water between 0 and 4 minutes. Interesting. All right, here's a really different kind. We have the same function up here. Again, it's got a dummy variable k, but we know that it equals 85. So we also know that this is the temperature of the water at the beginning. And this is how that water is changing temperature. And this is the result. So we can solve this equation and figure out how many minutes it takes for the temperature of the water to cool to 85 degrees Celsius. So this is an equation that can be solved to find K, the time in minutes, when the temperature of the water is 85 degrees Celsius. And this was another mistake they had that was supposed to, totally not right. Here, again, we have this dummy variable K, and again, we have this average factor. And when we look at this, when we look at this, we have an average. This is giving us just the temperature of 85. So this is an equation that can be solved to find time when the average temperature of the water is 85 degrees Celsius. Kind of interesting. These are all good interpretations that are important to know. All right, let's do some actual problems here. All right, let f be a function. Interesting. What is the average value of f on the closed interval from 1 to 3? Well, average value is 1 over b minus a. So here's our a and here's our b. So 3 minus 1 over the interval from 1 to 3. The integral from 1 to 3 of f of x dx. And again, could you do this by hand? Well, let's see. The derivative of sine is cosine, but I don't know. I don't think so. I'm thinking this is definitely a calculator problem. So we are going to plug this into our calculator. So I have 1 over 2 times the integral from 1 to 3 of f of x dx. Usually you get a point just for writing the integral. And they prefer you actually just use the notation instead of actually filling in sine of 2x times cosine of 1 plus x. Why? Because the more you write, the more chance you have to make a mistake. Potentially a copy error. Like you wrote 2 plus x instead of 1 plus x. And they don't want you to do that. So we have 1/2 times the integral from 1 to 3 of sine of 2x cosine of 1 plus x dx. And I get 0.369 approximately. All right, this is an interesting one. The average value of a function f over the interval from -2 to 3 is 6. Ladies and gentlemen, that entire little piece of a sentence is an equation. It is a math equation that says we're taking an average value from -2 to 3. So from -2 to 3 of our little f of x function, the average value, which we would do 1 over b minus a, so 3 minus a -2, is 6. Well, that's 1 over 5. All right. And then we also know that the average value of f over the interval from 3 to 5 is 20. Well, that's another equation I can write. Over the interval from 3 to 5, so 1 over 5 minus 3 of f of x dx is 20. Okay, so 1 over 2 times the integral of 3 to 5 is 20. Super. Okay, now they want to know what is the average value of f on the interval from -2 to 5. So they're trying to find, again, the average value. So 1 over b minus a, 5 minus a -2, the interval from -2 to 5 of f of x dx. Okay, that's what we want to know. Well, I know that that's 1 over 7. And the integral from -2 to 5 is really the sum of a couple of integrals. So let's see what we can do here. This integral is really the integral from -2 to 3 plus the integral from 3 to 5. So a little sum of two integrals equals the larger integral. That's true. So if we can figure out what the integral from -2 to 3 is, which is right here, how do I get rid of the 1/5? I'm going to times it by 5. I can do that. So the integral from -2 to 3 of f of x dx is equal to 30. Well, that's 30 then. All right. What's the integral from 3 to 5 then? Multiply by 2, we get 40. All right, 1/7 of 30 plus 40 is... Did I drop a negative again? I did. My God, that is the second time I've done that. -6, -6, -30. Oh, good Lord. Sorry about that, guys. All right. -30 plus 40 is 10. 1/7 of 10 is 10/7. All right. So, different kind of question. But it's important. Anytime you see the word is, it's an equation. All right. And you can see my error. Dropped a negative. Brilliant, right? Good God. I swear to God, I've done this like 3 times. All right. The intensity of light at a distance, x meters from a source. Intensity of light is modeled by the function r, where k is a positive constant. Which of the following gives the average intensity? Okay, average intensity, that's r right there, between 4 and 6 meters. All right, well, average intensity. Average, 1 over b minus a, and the integral from a to b of our intensity function. That's our intensity function is k over x squared. Okay, k is just a number. And we're going to integrate that. You can think about this as k to the -2 if you want. Increase the power by 1, we get -1. or negative k over x to the negative 1. There we go. And that is evaluated from 4 to 6. And remember here, where are we plugging in the 6 and the 4? In place of x. Yes. All right. So plugging in the 6, we get negative k over 6 minus the negative k over 4, which is letter C. All right. Oh, boy. Oh, Lord. Okay, ladies and gentlemen, this is the first full free response question. This is one free response question. It's not easy. I hope I can do it in 15 minutes. Okay. Mary and Chance walk in the same direction along a straight path. So we have Mary and Chance, and they're walking this long track in the same direction. Mary's velocity at time t is given by this function m of t, and it is a velocity function. Chance's velocity is given by c of t. So that's nice. Again, it's a velocity function. Really important to think about. Both m and the m function and c function are positive between 0 and 20 minutes and are measured in meters per minute. So these are the units. So Mary is walking so many meters per minute. Those are velocity units. And they're both positive, so they're going in the same direction. Positive to the right, that makes sense? Okay. And t is measured in minutes. Mary is 12 meters ahead of Chance at time t equals 0. So when Chance starts here at t equals 0, Mary's already 12 meters ahead of him. All right. So, and then she starts moving. Okay. We want to find the value of 1 over 10. Ooh, that's an average value there. From 5 to 15 of m of t dt. Using correct units, interpret the meaning in the context of the problem. Using correct units means that you would get a point for having those units on there. This is a 2-point question. So first we want to find the value of m of t dt. So 1 over 10, 5 to 15. So where did the 10 come from? Yeah, 15 minus 5. Okay. And again, this is something we can do in our calculators. So we would want to do that. And you'd have to. I mean, look at this crazy function. That is definitely not something we would want to try and do by hand. Since I have 2 functions here, I'm going to put this one in y1 and Chance's function in y2. And then I can just reference them. So 60/10 divided by, don't forget the parentheses, ladies and gentlemen. This is a common comment from the AP graders, is that the kids don't remember how to use their calculators. Make sure you're putting parentheses in that rational function there. I'm going to go ahead and enter Chance's function here too, 8.5 x cubed times e to the negative 0.45 t. Good Lord. Okay. All right. And I'm just going to quit. And now we can reference them using the vars menu, the variables menu, which on the TI is F4. I think on the Casio, you can pretty easily call up those variable like y1 and y2 also. I just can't remember. Okay. So here I'm going to do 1 over 10 and then integrate. Oh, whoops. Sorry, wrong thing. No, there we go. From 5 to 15 of m of t, I put in y1. So I'm just going to do alpha F4, and you can see it calls up our y1, y2, y3, y4. I want y1. So I'm just going to select y1, and it's using the equation in y1. All right, and I get 54.409. All right, what are the units? Well, let's think about this. M of t, the units were meters per minute. Meters per minute. We're multiplying the change in time. That's times more minutes. And then here, 1 over 10. 10 is also in minutes. And you can see the minutes cancel out, but we're still left with meters per minute. So this is, what does it represent in the context of the problem? This is her average velocity. Mary's average velocity between 5 and 15 minutes is 54.409 meters per minute. The graders give you 1 point for this answer and one point for the meaning with proper units. Okay. That's it. That's your 2 points. Okay. At time t equals 0, is Mary speeding up or slowing down? So this is something we haven't talked about in a while. I think we did this, you had this in Delta Math quite a bit. But to be speeding up, velocity and acceleration need to have the same sign. They either need to both be positive or both be negative. To be slowing down, velocity and acceleration have to have opposite signs. One's positive, one's negative. That means you're slowing down. All right. It's a good thing to remember. Velocity and acceleration have the same sign. They're either both positive or both negative. So what we need to consider here, again, this is a 2-pointer. The velocity is our equation here. So what is her velocity at 10 minutes? Well, that's pretty easy to figure out. We can go to our equation. Oh, actually, you want to know something interesting? I'm going to take 10 minutes and store it in x. And then if I take my equation, my y1 equation, it's going to evaluate it at 10 because it takes the x value that was last stored and just plugs it into the equation for you. Isn't that cool? Oh my God, my mind is blown. 49.876. What are the units on this? This is velocity, meters per minute. All right, this is a positive number, greater than 0. All right, now we also need to consider her acceleration. How do we find the acceleration? Well, it's just the derivative. The derivative of her velocity equation is acceleration. So I'm going to take the derivative. Going to the math menu, I'm going to take my numeric derivative, the derivative in terms of x, and I'm just using my y1 equation again, when x equals 10. And we get negative 7.036. Again, what is this? Meters per minute? Per minute. That's acceleration. That is less than 0. So are we speeding up or slowing down? Mary is slowing down because her velocity is negative. Her velocity is positive while her acceleration is negative. And acceleration is negative. Negative at t equals 10 minutes. You could probably say because her velocity and acceleration have different signs. That's probably good. All right. Is the distance between Mary and Chance at time t equals 18 increasing or decreasing? Oh, Nellie, I only have 5 minutes left here. Okay. How do we find the distance between these two folks? Given their velocity equations. Interesting. The distance between them is like their position equations. And so I'm gonna write a lot here. You don't actually need most of this stuff, but I think it's important for understanding. We're gonna let d of t represent the distance between Mary and Chance. Since t equals 0. All right. So how do we get the distance? Well, the distance would be knowing that they started 12 meters apart. Meters is a distance. All right. So Mary started 12 meters in front of Chance. And I only know her velocity equation in meters per minute. But if I integrate that, this is a rate. And if I integrate it, I'm going to get the amount of meters. So I'm going to integrate Mary's velocity equation. And that would give me her total distance way out here. The distance between them is to subtract Chance's distance. So I'm going to subtract Chance's distance. And again, we have to integrate because his is a velocity equation. Meters per minute. It's a rate. If we integrate, we get the amount of meters. Okay. So then, to tell if something is increasing or decreasing, that's a derivative, always. So what I want to do then is take the derivative at 18 to find out, is it positive or negative? If the derivative is positive or negative, then we know if our distances are increasing or decreasing. All right, so when I take a derivative and plug in 18, I'm going to do from 0 to k. That's 0 to k. K is a dummy variable. I'm going to put d of k here. There we go. So now that if we plug in some value for k and we're plugging in 18 in place of k, that'll give us the derivative at 18. Well, let's think about taking the derivative here. Derivative of 12 is 0. And the derivative of an integral, well, that's just the function back itself, right? That's kind of interesting. The derivative and the integral cancel each other out, and we're just plugging in that k value minus c of 18. And that's why I needed to go through this. All right, we're running out of time. All right, and we want to know what m of 18 minus c of 18 is. Let's see. I'm going to go ahead and store 18. I'm going to take 18. I'm going to store it in my x slot. And I want to do m of 18, so that's y1 minus y2, evaluated at 18. And I get not what I expected. Damn it. I'm not quite sure what it did. Okay. Let's do it the short way. 18, not the short way. Let's do it the long way. All right. I'm going to just do y1, and I get 18.752. And I'm going to do the same thing and do y2. Whoops. That's not what I wanted to do. Leave. Sorry. Okay. I'm going to do y2